everyone, myself Professor Khyati Gupta. Here in this video lecture, we will discuss about drug absorption. Now, what is absorption of drug? The process of movement of drug from its site of administration to systemic circulation is called absorption. Okay. So, when drug moves from site of administration, if it is topical or oral or IV, you administer the drug, right? And the movement of drug from the site of administration to systemic circulation is called absorption. Okay. Now, this figure shows you the rate and extent of drug absorption, right? Here on x-axis it is time and on y-axis it is plasma drug concentration, right? First slope, which is the higher peak slope, right? Chart, right? It shows you therapeutic success of a rapidly and completely absorbed drug, right? If the drug is rapidly and completely absorbed in systemic circulation, it will reach to higher concentration in the blood and its therapeutic level is high, right? So it reaches to its minimum effective concentration fast and reaches to higher concentration into the systemic circulation, right? But the drug which is slowly absorbed, right? It has therapeutic failure, right? It doesn't reach to its minimum effective concentration and it doesn't show any physiological response. Okay, so this figure shows you significance of rate and extent of absorption in drug therapy. Okay, next is mechanisms of drug absorption. Okay, there are mainly three categories of drug absorption mechanisms. In that, first is transcellular or intracellular transport, in which it includes A, passive transport process, and B, active transport process. And further, these two, passive and active, are further subdivided into categories, in which passive transport process includes passive diffusion, pore transport, ion pair transport, and facilitated or mediated diffusion. Okay, and active transport process includes primary and secondary transport processes, in which secondary transport processes is further divided into two, symport and antiport process. Okay, second is paracellular or intercellular transport, in which first category is permeation through light or junctions of epithelial cells and persorption. Okay, and next is vesicular or corpuscular transport, or you can say endocytosis, in which first category is pinocytosis and second is phagocytosis. Okay, we will discuss all these categories in details, right? Now, this is the difference between transcellular, paracellular and vesicular transport. Okay, in which transcellular is divided into passive diffusion. Your first figure shows you the passive diffusion, okay, in which carrier is not necessary. Okay, and the second is carrier mediated transport, in which C indicates you carrier. Okay, second is paracellular figure, right? And last one, third, is vesicellular, in which you can see the endocytosis process. Okay, we will understand this all mechanisms in detail. Okay, now first is transcellular or intracellular transport. Okay, it is defined as the passage of drug across the GI epithelium. There are three steps involved in this category. First is permeation of GI epithelial cell membrane. Second is movement across the intracellular space. And third is permeation of the lateral or basolateral membrane. Okay. Now, various transcellular transport processes are, first is passive transport process. As we know that passive diffusion does not need any energy. This passive transport process further classified into four types, in which first is passive diffusion. It is also called a non-ionic diffusion. It is the major process for absorption of more than 90% of the drugs, right? More than 90% of drugs are absorbed by passive diffusion. in which driving force is concentration or electrochemical gradient. Now, passive diffusion is defined as the difference in drug concentration on either side of the membrane, and it is best expressed by Fick's first law of diffusion, which states that drug molecules diffuse from a region of higher concentration to one of the lower concentration until equilibrium is attained. Okay, where the drug is in higher concentration, the drug flows towards the lower concentration of drug. Okay, and this process is called passive diffusion. Now, the rate of diffusion is directly proportional to the concentration gradient across the membrane, which states by the equation dq by dt is equal to dak m by w upon h in bracket cgit minus c, in which dq by dt means rate of drug diffusion, d indicates diffusion coefficient of drug, a indicates surface area of absorbing membrane, Km by W, partition coefficient of drug membrane and the aqueous phase. Cgit minus C indicates difference in the concentration of drug in GI fluid and in plasma. Okay, and H indicates thickness of the membrane. Now, second one is pore transport. It is also called as convective transport, bulk flow, or filtration. Right? Now, the driving force here is hydrostatic pressure or the osmotic difference across the membrane. The process is important in the absorption of lower molecular weight, less than 100, generally water soluble drugs, right? This pore transport process is for generally water soluble drugs whose molecular weight is lower, less than 100, right? Chain-like or linear compounds of molecular weight up to 400 Daltons can be absorbed by filtration. For example, the straight chain alkanes, right? Drug permeation through water-filled channels is important in renal excretion, removal of drug from cerebrospinal fluid, and entry of drug into the plasma. Okay, so pore transport is convective transport or bulk flow. Generally, a water-soluble drug can flow through this process, right? And generally linear compound or molecular weight up to 400 Daltons can be absorbed by filtration. Okay, next is ion pair transport, in which absorption of drugs like quaternary ammonium compounds and sulfonic acids which ionize under all pH conditions is ion pair transport, right? So the drugs which can ionize can diffuse through this process. Okay, despite their lower oil water partition coefficient values, such agents penetrate the membrane by forming reversible neutral complexes with endogenous ions of the GIT like mucin, right? Here you can see in this figure, the plus indicates cationic drug and the minus sign indicates endogenous ion, right? This drug is now located into the GIT lumen, right? These both anion and cationic drug will make a neutral ion pair complex, and this ion pair complex can diffuse through a membrane, right? And when it reaches to blood, it will dissociate and further it will free the drug molecule, right? So such neutral complexes have both the required lipophilicity as well as aqueous solubility for passive diffusion, and such a phenomenon is called ion pair transport. Example of this process is propranolol, right? Propranolol drug is diffused through ion pair transport mechanism, right? Fourth is carrier mediated or facilitated diffusion. Some polar drugs cross the membrane more readily than can be predicted from their concentration gradient and partition coefficient values, like monosaccharides, amino acids, and vitamins will be poorly absorbed, right? These drugs are polar and they cross the membrane more readily than we predict, right? How? What is the mechanism? Here, the mechanism is involved is carrier that binds reversibly or non-covalently with the solute molecules to be transported, right? This carrier solute complex traverses across the membrane to other side where it dissociates and discharges the solute molecule, right? The carrier then returns to its original site to complete the cycle by accepting a fresh molecule to solute. Carriers in membranes are proteins and maybe an enzyme or other component of the membrane, right? Here in this figure you can see in GIT vitamin B12 and intrinsic factor complex binds to carrier which is located into the membrane, right? It binds to this vitamin B12 intrinsic factor complex and will make a complex, and it diffuses to other side of the membrane when where it free the vitamin B12 and intrinsic factor complex, and this both also liberates into the blood, right, individually. Okay, so it is carrier mediated or you can say facilitated diffusion. Okay, this type of diffusion is much faster than simple passive diffusion. Okay, but here driving force is a concentration gradient also. Okay, since no energy expenditure is involved, the process is not inhibited by metabolic poisons that interfere with the diffusion. Okay, this graph indicates you passive diffusion and carrier mediated diffusion, right, where your y-axis indicates rate of drug absorption and x-axis is concentration of drug at the absorption site. Okay, so rate of drug absorption in carrier mediated transport is higher than passive diffusion. Okay, now second is active transport processes. This transport process requires energy, right? Active means it requires energy and passive does not require any type of energy. Now, active transport process require energy. How it will get energy? It will get energy from ATP molecule, right? To move drug molecules from extracellular to intracellular milieu. Okay, there are of two types of active transport processes. First is primary active transport, right, in which there is direct ATP requirement. Moreover, the process transfers only one ion or molecule and in only one direction and hence called unipolar. Absorption of glucose is the example of this type of process. Okay. Second is secondary active transport. In this process, there is no direct ATP requirement. It means it takes advantage of previously existing concentration gradient. The energy required in transporting an ion aids transport to another ion or molecule. It means co-transport, right? Either in same direction or in opposite direction. Accordingly, this process is further divided into two, symport and antiport. In symport, it involves movement of both molecules in the same direction, right? For example, sodium and glucose symporter. And in antiport, it involves movement of molecules in opposite direction. For example, hydrogen ion using the sodium gradient in kidneys, right? We will understand this by figure, right, in which this is the drug complex, means carrier mediated, right. Next figure is see here concentration gradient is moving into upwards, right, upward direction. Okay, how now primary active transport needs ATP, which is a direct requirement, right. Now it travels through low concentration to higher concentration. Okay, and therefore it requires energy or ATP, you can say. Now in secondary active transport, first figure shows you symport, right, in which flow through higher concentration to lower concentration. Therefore, it doesn't require direct ATP, right? And both the flow are in same direction. Therefore, it is called symport. Okay, and in antipode, the direction is opposite, right? First molecule flows through one direction and second molecule flows in opposite direction of the first. Okay, so in secondary active transport, in first process it requires energy, but in second process it doesn't require energy because it will use the concentration gradient of first, right? Now, second process is paracellular or intercellular transport, which is defined as transport of drugs through the junctions between the GI epithelial cells. We know that these are the tight junctions of GI epithelial cells from which the drug molecule transports. This pathway of minor importance in drug absorption, right? The two paracellular transport mechanisms involved in drug absorption are: first is permeation through tight junctions of epithelial cells. This process basically occurs through openings which are little bigger than the aqueous pores. Okay, we have tight junctions between epithelial cells. Therefore, the space between the epithelial cell junction will be much smaller, right? So, compounds like insulin and cardiac glycosides can be transported through these pores, right? Therefore, this mechanism is of minor importance. Okay. Persorption. It is the permeation of drug through temporary openings formed by shedding of two neighboring epithelial cells into the lumen. Okay. And third and last is vesicular or corpuscular transports, which means endocytosis. Now, like active transport, these are also energy dependent processes but involve transport of substances within vesicles into a cell, right? Since the mechanism involves transport across the cell membrane, the process can also be classified as transcellular. Now, this phenomenon is responsible for cellular uptake of macromolecular nutrients like fat, starch, oil-soluble vitamins like ADEK, water-soluble vitamin like vitamin B12, and drugs like insulin. Other significance of such a process is that a drug is absorbed in lymphatic circulation, thereby bypassing first pass hepatic metabolism, right? This can be classified into two categories. First is pinocytosis, which means uptake of a fluid solute, and therefore it is called cell drinking. And second is phagocytosis, uptake of solid particulate, and therefore it is called cell eating, right? We will understand it by figure. See, in GIT we have a macromolecule, right? And the membrane will engulf this molecule and make a vesicle around the molecule, right? And on the other side of the membrane, it will release the molecule from this vesicle, right? So this process is called vesicular transport. Okay, thank you for watching this video.